In this video, we'll talk about factorization machines. Since we're talking about SageMaker, which is end-to-end machine learning solutions built on top of AWS, where training, evaluation, monitoring, and deployment of machine learning algorithms can be implemented easily. Major advantage of SageMaker is that it has built-in machine learning algorithms. To feel the power of SageMaker characteristics, we shall be taking an example of powerful model hosted on SageMaker, which is often referred to as factorization machines. The factorization machine algorithm is a general purpose supervised learning algorithm which can be used for classification and regression. It is an extension of linear model which is designed to capture interactions between features within high dimensional sparse dataset economically. For example, in a click prediction system, the factorization machine model can capture click rate patterns observed when ads from a certain ad category are placed on pages from a certain page category. Factorization machines are a good choice for tasks dealing with high dimensional sparse dataset such as click prediction and item recommendation. Now let's see how factorization machine work. The prediction task for factorization machine model is to estimate a function from a feature set to target domain. The domain is real valued for regression and binary for classification. The factorization machine model is supervised. The advantage of this model presents in a way where it uses a factorized parameterization to capture the pairwise feature interactions. It can be represented mathematically as follows. The three terms in the equation corresponds respectively to three components of the model. The W0 term represents the global bias. The Wi term represents linear term model, which is the strength of the ith variable. The Vi and Vj factorization terms models the pairwise interaction between the ith and jth variable. The global bias and linear terms are same as linear model. The pairwise feature interaction are modeled in third term as the inner product of the corresponding factors learned for each other features. Learned factors can also be considered as embedding vectors for each feature. For example, in a classification task, if a pair of feature tends to co-occur more often in positive labeled samples, then the inner product of their factors would be large. In other words, their embedding vectors would be close to each other in cosine similarity. What distinguishes factorization machine also is it can work on both classification and regression problem. So we will try to use it to tackle our problem with both approaches. In this video, we'll be talking about Amazon EC2. Amazon EC2 provides the following purchasing option to enable you to optimize your cost based on your needs. The first is on-demand instances. Pay by the second for the instance that you launch. The second is saving plans, which is to reduce your Amazon EC2 cost by making a commitment to a consistent amount of usage in USD per hour for a term of 1 or 3 years. The third option is reserved instances, where you can reduce your Amazon EC2 cost by making a commitment to a consistent instance of configuration, including instance type and region, for a term of 1 or 3 years. The last option is spot instances, where you can request unused EC2 instances, which can reduce your Amazon EC2 cost significantly. Let's also look into some other EC2 purchasing option. The first is dedicated host, where you pay for a physical host that is fully dedicated to running your instances and bring your existing per socket, per core, per VM software licenses to reduce cost. The second is dedicated instances, where you pay by the hour for instance that run on single tenant hardware. The third option is capacity reservations, where you reserve capacity for your EC2 instance in a specific availability zone for any duration. Let's see how we can choose EC2 instances. If you require a capacity reservation, purchase reserved instances or capacity reservation for a specific availability zone. Spot instances are a cost-effective choice if you can be flexible about when your application can run and if they can be interrupted or not. Dedicated host or dedicated instances can help you address compliance requirements and reduce cost by using your existing server-bound software license. One of the choices that can lower your cost while training machine learning model is using spot instances for training. So let's see how spot instances work. A spot instance is an unused EC2 instance that is available for less than on-demand prices because spot instances enable you to request unused EC2 instances at a steep discount. You can lower your Amazon EC2 cost significantly. The hourly price for a spot instance is called spot price. The spot price of each instance type in each availability zone is set by Amazon EC2 and is adjusted gradually based on the long-term supply of and demand for spot instances. Your spot instances run whenever capacity is available and the maximum price per hour for your request exceeds the spot price. Spot instances are cost-effective choice if you can be flexible about your application run and if your application can be interrupted. For example, spot instances are well suited for data analysis, batch jobs, background processing, and optimal tasks. When we will be tackling our Amazon review project, we will see the difference between both approaches in training, on-demand EC2 and spot instances. In this video, we'll look into how do we train the model. We will use Amazon SageMaker training job for that. Amazon SageMaker training jobs are an easy way to create model as you don't really have to write all the code for the training. That is already handled for you in a nice container format. The general workflow for creating training jobs from the notebook is to instantiate the predictor, pass some hyperparameters, and then pass the data in the correct format. This is what happens in the following cell. Let's understand a bit about this code. We start by importing getExecutionRole and image URI. We also define the output prefix which we want the model to be stored in our S3 bucket. We have to also give the instance type which is Amazon EC2 instance. Be very careful, you will be charged for this if not budgeted well. We then simply create an execution role for SageMaker to run the model. Then we define the estimator and load the factorization machine. Next is to set the hyperparameters for our model like passing our features, type of problem which is regression in our case, the batch size which is 128, total number of factors or column which is 64, epochs as 25, clip gradient as 5, and the last is rescale grad which is 1 divided by batch size we have. Now all these parameters are currently set as standard values. You can obviously change it to make sure that you get best models out of it. It has to go through a lot of trial and error to figure out the best parameters that will go better with your data. So don't take these numbers as the standard numbers. For all different kinds of data that you will be using in future or for any other problem that you're trying to solve, these numbers might change, which means you have to play with these numbers, try out different combinations, and then see which one gives you better results. Once all the parameters are defined, we can simply call the .fit function on our FM object and pass the train and test path of the data. You will start noticing that it will print a lot of things while training is going on, and that is absolutely normal. Make sure that you see something like this, which means and which shows that our training is in progress and there's nothing wrong and everything is working as expected. Towards the end, you will get the final success message confirming that the training job completed, which means your model is ready and saved in S3. This means that whatever data that we started off with and whatever we were trying to predict has been properly leveraged using factorization machines and using SageMaker. Quick basic comments about SageMaker that you need to remember is that it is very easy to implement, where you just have to load the desired estimator and the hyperparameter. Here you can observe that the training process will cost us 153 or 240 seconds of EC2 computation. Do you think we can save more money on the training job? Do you think there are a few things we can change that can help us save more money? Now in the previous video, if you remember, we had asked a simple question: can you save the cost of computation on EC2? Let's see in this video how by simply doing one single line change, you can save up to 60% of the cost. In the code that we have written in the previous video, all we have to do is we have to change these 3 lines or add them if they are not already added, which is use spot instance equals to true. This will indicate that we are now using the spot instances. Then we mention the max run to be 900, which is the max time for the whole model to run. If the training takes longer, imagining if you have a bigger data, it will then be terminated. Then the max wait, which is 1200. Again, this is a max time to wait for spot instances to become available. Keeping everything as it is, you can see that we are able to save up to 62.3% of the cost. That's really amazing because the total billable seconds now is 87, and that's the power of spot instance. Do remember that they come with their own challenges. If you're working on a very huge dataset, you have to make sure to edit max run and max wait parameters to use spot instance efficiently. Till now, we have successfully launched an Amazon SageMaker training job. Now we will try to evaluate the model. To do that, we'll start by calculating a naive baseline to approximate how well your model is doing. The simple estimate would be to assume every user item rating is just the average rating of overall rating. This is basically saying that you have model that only learn to output the mean value of the reviews. To do that, now let's first start by calculating the naive guess, which is just taking a mean of all the star ratings and then simply doing the difference between actual test data star rating and the naive guess, and then doing the mean of it by squaring all the results. This will give us naive MSE to be around 1.5. Now that we have a simple evaluation, to get the actual MSE, we need to first deploy the model. In this video, let's talk about deployment, as we always need to deploy a model as the last step of any machine learning problem. Deployment is very easy to do in SageMaker. It's just a single line of command. We can simply do fm.deploy, in which you need to define how many instances you need and what would be the instance type. Now you can see that in this you have, after running fm.deploy, you have created an API for inference. You can investigate it by navigating training to endpoints. Our model is deployed on one instance initially because we have passed initial instance count equals to 1. Also, the model is using M1 X4 XLarge machine for the deployment purposes. Now, to get a prediction, we need to pass the data in serialized form of JSON. The output you get from the inference will be serialized JSON form as well. So you also need to deserialize it to get to the predicted values. To do that, you need to create a serialization function for the predictor. We simply create a class fmSerializer and define the base content type as JSON. We then add an instance method or function which takes each input data and simply appends to empty JSON variable that we have created. Finally, we return the JSON.dump for all the input serialized data. As you can see, the accepted content type is JSON once you call and print the fmpredictor.content type. Now, let's see how our training set did. You can use the endpoint to get the prediction from your model. Do remember that the Amazon SageMaker model containers must respond to requests within 60 seconds. The model itself can give a maximum processing time of 60 seconds before responding to the request. To do that, call the predict function for 5 rows at a time and then add those rows in a list. What we have done here is we are writing a for loop and we are making sure that out of 1000 data, we are sending 5 data at a given moment into fmpredictor.predict. You can see that we are converting this into arrays, and once we get the prediction, we are saving it into preds. This pred finally goes to append in the ytrain.p, which is going to save all the results. Let's do a sanity check and see what are the minimum and the maximum values for a score. Do remember that we already have these actual values. You can see that the minimum rating predicted is negative 0.2 and the maximum is positive 1.4. Again, this is on a trained data. Now let's do the same thing on the test data. So you can see that the minimum and the max in the test data is somewhat very similar, which is min is 0.7 negative and positive is 1.3. Like I said, this is not very different, and which is a good sign, which means that the model is being consistent on both train and test. Now that we have done this, we can now simply measure the MSE of the test data by using the same function that we have been using to create the MSE score, which subtracts the test and the yPredict, which is the prediction that the model has done. And you can see that we are getting 13.890 as the MSE. Now, the MSE of 13.89 is neither good nor bad. It simply means that we are able to do better than the guessing. which means we might want to make sure that our models are tuned properly to get better results. Now let's try to predict for some random users and see if the results are making sense. To do that, we can filter a random user, let's say 210. You can clearly see from the data that the user likes action movie. Now we have to go through the same steps that we have taken so far in the previous videos, which is converting this user data to first pass matrix. We can use the function that we have written previously, which is prepare prediction, which takes the user ID, number of movies, and does the same lil matrix usage to convert this into a sparse matrix. This will return the features which will then be used to pass to a prediction function. Once you have that, you can see that we are now using user 210 data and we are passing that into the same for loop that we have defined and passing only 5 records at a moment. We are again saving the predictions into pred 210. Now to see the results, what we're going to do is we're going to create a new data frames title by using reduce df data frame to group by items. For that, we are going to use product title column and create another column score and add the values from pred 210 to it. Now we can see some of the sample scores that the model has predicted for this user. Let's do more validation and see how well our model generates scores and see how the predictions of another users are correlated with user 210. We can use the same steps we have done for 210. This time we can pass 200 because we have created that function to be generic, which means you can pass any user ID and then it will do all the things that we have done for 210. So in this we are calling a prepare prediction, passing a specific ID which is 200, and you can see that we are now getting the results saved in user 200. We're going to do the same for loop, again passing 5 records at a moment, and then we save all the predictions into predict 200. We simply do a plotting of scatter plot by passing the predictions of 200 and predictions of 210. These are two different users. You can simply make sense that the predictions of two different users are perfectly correlated. Now let's try another approach, and also before moving forward, let's delete the endpoint. To do that, you can simply do sagemaker.session and then delete endpoints and pass the endpoint name through the FM predictor variable. Now that we have a model that is deployed into two production variants, we want to monitor the model performance, again number of requests, in what is known as load test generally. We will send a model huge number of data in small time intervals and check how it is performing under that stress. To do that, we simply start by defining NB connections, which is total connections that are going to be accepted by the SageMaker prediction. Next, we need to make sure that the SageMaker runtime can accept 200 connections. We can simply change the Boto client config by passing max pool connections and then passing the NB connection value to it. Next, we create a simple send data function which will take the data from our trained data and use fm prediction.predict function to run the prediction. Finally, we define a load test endpoint function which will initiate the load test. We run a simple for loop which runs till the NB repetitions, which are total repetitions of 200 connections we want it to run. We also keep a with condition to make sure that it creates that many threads to be executed through endpoints. We then simply run another for loop to each thread where it sends the prediction and tests if the deployed model is able to predict in this stress. We're also measuring the time so as to be aware of how much time it takes for 200 requests. Finally, we can call the function and mention how many times you'd like to repeat this load test as NB repetitions and pass the NB request also dynamically. You can see that it roughly takes 3.5 seconds to run 200 predictions through our current model. As we are loading our models with requests, we can go to the endpoints and add the monitoring graph to the CloudWatch as well. In this video, let's try a different approach. Now what we are going to do is we're going to change the training dataset to have binary output depending on the rating that they get. You will consider recommending something to your user when the rating is 5 stars, and you will save again as a protobuf format in Amazon S3. To do that, we'll start by using the load dataset function with the option regression false to create your training dataset. Then we will write the dataset as a protobuf format. The third step would be to retrain your model using predictor type equals to binary classifier. Then following that, we will do a deployment of the model to an endpoint and evaluate the model similar to how we did before on the test set. We'll finally inspect how we did on the test set using a confusion matrix. So you can see that we have already done the load dataset part by regressive false, and we are also writing the dataset to protobuf. Finally, we'll retrain the model changing from regression to binary classification. Again, we are using the same code and setting that you did when we were training the model previously, but we are changing predictor type to binary classifier. Also, don't forget to use spot instance for cost reduction. As you can see that the training is going on and there is no issue so far. Everything is being printed in blue, which means that there's no issue and error so far in the training. Finally, once the training job is completed, you can see that by using spot training, we were able to save 65.4%. The next step after the training of the model, we will evaluate the performance of this model. We will deploy and determine the serializer and then pass the test data. To do that, we can simply do fm.deploy, mention the initial instance count, instance type, pass the serializer, which is what we have defined in the previous video, which is fm serializer. And the deserializer has to be JSON deserializer here. Once we have defined the predictor, we can simply now go through each test data and again sending 5 records a time. And we can call the predictor and pass the data and save the predictions back to preds and finally to y_pred. To inspect how well the classifier is doing, we can calculate and plot a confusion matrix. We can use the implementation of scikit-learn here because we already have the true values and the predicted values. What we are also trying to do here is we are creating the predicted as binary, which means that if the value is greater than 0.5, we're going to call it as 1, L0, so that it is easier for confusion matrix to plot this. Once you do that, you can see that now we can simply calculate the accuracy, and you can see that the accuracy currently we are getting is 69.3%. The model is doing significantly better than the naive model, which randomly generates an output roughly around 50% accuracy. If you look closely to the confusion matrix, the model is being conservative and preferring not to recommend things to user. That means most of the mistakes the model is making comes from not recommending movies to user. And finally, like we saw, before we do anything else, we first need to make sure that we delete the endpoint. To do that, we can simply use the function delete endpoints and pass the endpoint from fm predictor. Let's try to run a hyperparameter tuning job to improve the model a little bit. Hyperparameter tuning is one of the most important features in SageMaker. In general, there are 3 main approaches for this. First, which is grid search, where it constructs a grid with all possible combination, and then it tries to search for all of this to check for the better accuracy. Do remember this is computationally very expensive as it is trying out each and every combination. The second is random search, where it picks some random values of the whole possible grid or possible values that you want it to try. This is less computationally expensive than grid search. And the last is Bayesian search. This is the best of them all. It uses probability distribution to decide which values may have the best metric. To trigger hyperparameter tuning job, we can use the tuner module of SageMaker. The first step is to define the parameter range that we want to tune. In this case, we are using bias init scale and bias LR, where we are passing the continuous parameters and we are asking the tuner to try out all the values between 0.1 to 10. And we are asking it to scale it through a logarithmic scale. Same for the bias LR, where we are asking it to try out all the values between 0.01 and 1, and the scaling should be logarithmic. The next step is to define the objective matrix and the objective type. In this case, we are saying it to be classification, and we are trying to tell it that please maximize the accuracy. This is important because if you were to do regression, in that case, you would then mention the metric name to be MSC. The next step is to finally pass all the arguments into the hyperparameter tuning function. You can see here we are passing our FM, we are passing the objective metric name, the ranges, the max zob, which means we are explicitly telling it to only try out 10 different parameters. We're also asking it to do a parallel job here, and then the objective which we have defined previously. You can finally fit the tuner by using tuner.fit. Do remember that the job will run in background, so as to see the status, we'll do the following things. To start, we will first initially use sage client.describe hyperparameter tuning job, which will save the current status of the job in tuning job result. Then we simply check if the status is not completed, we will simply print tuning job has not completed. If it is completed, we'll print the results that it has achieved so far. You can see that very clearly that it shows 10 training jobs have been completed, and it tells us that what is the current parameters which has shown to be giving better accuracy. In this case, currently we're getting 69.79, which is better than what we were getting in the previous case. You can also see the bias init scale and the bias LR value, which is currently 0.64 for bias init and bias LR to be 0.01. This combination is giving us 69.79. Now, suppose we have the following situation where we have a model that is already in production, which is our last model, and after tuning the model a little bit, we now have a new tuned model. To make sure that the tuned model is better, we will do what is called as A/B testing, and it simply means that we will have two models into production, and half of the traffic will be directed to the old model and the other half of the traffic will be directed to the new model. Until we make sure that the new model is reliable, we will keep directing all the traffic to either one of the models. This concept can be used by using production variants in the SageMaker. To do that, first what we're going to do is we're going to create a SageMaker model from the best model. To do that, we can simply do create model from job, passing the tuner that we have just created in the previous video, and then get the tuned model. Now we first get the current endpoint configuration by again using describing the endpoints and getting the current endpoint into the endpoint config. Now the first thing that we need to do is we need to change the weightage of the current model to 0.5. To do that, we can simply get the endpoint config, in that get the production variant, and change the initial weight variant to 0.5. We can also change the name of this model to current FM. Now we create a configuration for the tuned model which will run on the other half weightage. So we define it to be tuned model name, which is the model that we have created. Then we define the initial instance count, which is 1, define the instance type, the variant name, and the weight variant, which is 0.5. Now we simply create a new endpoint configuration with two production variant, which is current model and the tuned model, by using production variant and passing these two models into that. Once you have that, you can simply update the endpoint by using .update endpoint and passing both the names, endpoint config name and the AB config. Once you have that, we can simply use .session and wait for endpoint to make sure that it is finally running. As a result, now you have two endpoints with two production variants. Let's take a quick summary of all that we have covered in this course. We've talked about factorization machines. We've talked about EC2 instance selection. We also saw model training, evaluation, and deployment tutorials. And finally, we have seen model tuning and testing tutorials. Coming up next is AWS AI services and SageMaker applications.